Okay, let's start. Hello, and welcome to Math 4800, undergraduate research. Hey, undergraduate research in math, and this semester we're going to focus on fractal geometry and dynamics. Before I go any further, obviously I'm recording this class, but I mean, some of you have taken classes from me last semester, for instance, and you know that I do record and I put things on YouTube, but I'm going to make sure that it's all anonymized. So, it's not an issue if you sort of go up and, go to the bathroom and stuff like that. Eventually, I'm going to figure out the physicality of this room better. So there's going to be more space and everything. So that's that. My name is Alp. And as an email, you can use my last name, Uzman, at math.utah.edu. So this class meets twice a week. I mean, you all know this, but still. And each lecture is 80 minutes long. So at this point, I don't really see an issue with that, but it might turn out that maybe sort of like a 5-minute bathroom break might be good, or something like that, because I haven't taught a class that was this long ever. So I'm just learning as we go. So today I'd like to go over the syllabus and a little bit over the first report, 0th report, I guess. That's due this Sunday. And then if you have time, I'm sure we're just going to start talking about the topics. So Math 4800 is an introduction to research in math. As outlined in the general catalog, it is worth 3 credits and has listed instructor consent as the only prerequisite, which you all know, because each of you have corresponded with me over email. The idea of an introduction to research course might seem paradoxical, as conducting mathematical research differs significantly from taking a math course. The fundamental difference lies in the stance and attitude one must adopt. While a standard mathematics course is structured with well-defined tasks and a straightforward path, research is more open-ended and subjective. Now, as you can figure out, perhaps I had to think a lot about how to teach this class. Math 4800 aims to blend these two approaches. While the course includes lectures and weekly graded assignments, it also incorporates open-ended, student-driven projects, collective assignments, and a final written project and oral presentation instead of a final exam. And I'm asking all written submissions to be prepared in LaTeX or LaTeX. How many of you have experience with LaTeX or LaTeX? Okay, so that's good. If you don't know how to use it, that's still okay, because this week's report is just going to be a practice. So you'll be able to learn it. It's not super complicated to start, but of course it's very deep. Okay, this semester's Math 4800. Okay, each semester, Math 4800 focuses on a particular topic. This semester, we will investigate fractals and dynamics, as I wrote here. Fractals are objects that appear similar at different scales, and dynamics is the mathematical study of time evolutions of closed systems. Now, I am a professional mathematician. I'm a postdoc here, and my field of expertise is dynamics, really, a certain type of dynamics. But one ends up needing to use some ideas from fractal geometry, in particular this notion of dimension. Often a fractal is a residue of a dynamical system that has evolved over a long time. For example, the Barnsley fern, this is popular among computer scientists, is the attractor of a specific iterated function system. All of these terms we're going to learn. And the Mandelbrot set is determined by whether the trajectory of a seed runs off to infinity under a certain dynamical system. We're going to spend plenty of time on iterated function systems, IFS for short. Mandelbrot sets, I don't think we're going to cover in class, But it's a chapter in the book, in the main book, and that's a possible sort of research if you want to look into that during your weekly reports or the final report. Okay, this deep connection between fractal geometry and dynamics makes studying these two subjects together fruitful. While there are many applications of fractal geometry and dynamics, our starting point will be from a pure mathematics perspective. Explorations of applications will be admissible for assignments. Now, I am a pure mathematician by training and by occupation, but if you're into applied stuff more, I'll try to be as accommodating as possible, and I'll try to sort of work with you on whatever you want to do. There are many applications of fractals and dynamics as well. So for instance, one application that is discussed in the main book is what are called fractal interpolation. So you have, let's say, an image, and you want to sort of compress the image. So you can use fractals sort of to handle that. And there are other things as well, if you're into neural networks or some other things. I'm just going to skip prerequisites. Basically, I'm asking you to have some understanding of calculus, and of course, these epsilon-delta stuff. Because we're going to use a lot of analysis, basically, and you're going to have to get comfortable with those, even if you're not super comfortable with them now. Familiarity with topology and measure theory of metric spaces will be beneficial but not necessary, as we will develop what we need in the course. So these are sort of two contexts in which you can think about metric spaces. Metric spaces are just spaces where there's a defined notion of distance between points. Okay, you are expectations. As a student, you are expected to attend all lectures, complete weekly reports, complete a final report, and give an in-class presentation of your final report. Fairly straightforward. Workload is 6 to 9 hours per week as per the university regulations, but maybe you know everything too well and you don't need to study that much. So then it's like 4 hours, or maybe you're too interested in something and like 9 hours doesn't quite cut it, or you want to do something more advanced or something like that. That's basically, that depends on you. Okay, learning objectives. We have two types of learning objectives. One of them is because of the title. This is an introduction to research. So the first type of objectives relates to the course being an introduction to research. These objectives include learning how to study topics that are complementary to the material covered in class. So this is this idea, the complementarity, right? Like if you're taking a standard class, you would expect that whatever in class we talk about, the exercises are about those. But in this class, exercises, basically you're going to decide whatever you want to study, as long as it is related, obviously. So you get to choose your own path, in a sense. Study topics in a collective fashion. I'm going to discuss this more a little bit in a second. Choose a topic to study within a limited amount of time. So let's say that you want to prepare a weekly report, let's say in week 5, and you look at the textbook and there's this exercise or some other topic that you think is nice. But of course, part of it is to be able to come up with something and type it down and everything within the limited amount of time, limited period. So that's sort of like an important thing to be able to think. Use a document preparation system, LaTeX, or LaTeX. Present what you have learned, discovered, or invented, both in speech and writing, in a way that meets contemporary standards of mathematical rigor and presentation. And of course, this notion of rigor depends on what exactly you're doing. If you're doing something, pure mathematical, the rigor is slightly different. Whereas if you're doing something more applied, like what the rigor there is it changes a little bit. The second type of objectives pertains to the specific topic of fractal geometry and dynamics. These objectives include learning how to work with metric spaces in terms of uniformity, topology, and measurability. These are 3 contexts in which looking at metric spaces will be useful for us. work with the Hausdorff distance. This is like a very specific type of metric space, where it's part of a specific type of a metric space. Prove and apply the Banach contraction principle. Think from a dynamical point of view, where you think of symmetries as time, which is perhaps paradoxical or weird a little bit to say, but that's sort of like the dynamical point of view. Use iterated function systems to understand complicated shapes with some self-similarity. And I feel like at this stage I should say at least one thing about this iterated function system business. How many of you have seen this Cantor set? Okay, a couple of you. So there's this idea, which goes back to Cantor, and it's a certain subset of the real line. So what you do is you take a line segment, and then iteratively you keep taking away parts of it. So this is step 0. At step 1, what you do is this. You divide this interval, let's say it's from 0 to 1, you divide it into 3 equal segments, and then you get rid of this middle piece. Okay? The other 2 pieces remain. Okay, so. And then the next stage, somewhere over here, you do the same thing to each one of these pieces. Okay? So now you divide this piece into 3 pieces, get rid of the middle piece, and now you have this and this, and then you do the same thing here. And then at stage 3, you do the same thing to each one of these smaller pieces and so on. And ultimately, in the limit, you get something which is like a bunch of points. It's a certain set where it has infinitely many points in it, but no 2 points are connected via a path. It's a thing. It's a set. And the IFS business, iterated function system business, comes into play where you sort of like look at this picture from a more functional point of view. You want to say, oh, you want to sort of make it more rigorous in a sense, more formal. You say, oh, how do I turn this interval into 2 smaller intervals? Well, you can say I have 2 contractions, so 2 functions. One of them takes the interval and turns it into this smaller interval. So let's call this f1. So I can write a formula now, right? f1 of x, what is that? It's a function, so it has to depend on x.
X over 3.
Yep. And I have another guy, f2, that does the same thing. It contracts, but it sort of puts it over here. So what is this?
Did you do 1 minus x over 3?
Yeah. Yeah. Well, okay. Geometrically it is correct, but the thing is that you're flipping the interval. You don't want to do that. So you want to say something like x over 3, but then shift this way. So you're basically correct, but let's write it like this. X over 3 plus 2 over 3. Okay? So now I can say, oh, I get to apply the same 2 functions to pieces here, or to this interval, or to this interval. I can keep going, right? So applying f1 to this piece does this, or applying f2 over this piece does this other thing, and so on. So at each step, you're really applying 2 of these, either one of these functions, and ultimately you end up with something. So this idea that instead of focusing on this Cantor set, focusing on the whole process is the IFS, is the idea of the IFS. So we're going to spend a lot of time on this, but you would say something like, my IFS is f1, f2. Okay, that's a simple example. And there are, of course, other examples there's this triangle example, for instance. Let me just write it here. Sierpinski carpet, I think, is the name. And it's the same idea, except that this time you start with a filled-in triangle, and then at the next step, what you do is you sort of divide it into smaller triangles, get rid of the middle piece, and so on. Same idea. And then you keep going. And as you can see, you can also think of this in a similar fashion. You would say, I have three contractions, F1, F2, F3. One of them contracts by, I guess, one half, puts it over here, the other one over there, the other one over there. Okay, same idea. So this turns out to be a very useful way of thinking about these things, these fractals. Because instead of saying, okay, so this is the end result, which is this fractal itself, you talk about how it came to be, really. And already at this stage, you can sort of see the connection between fractals and dynamics. Okay. Use symbolic dynamics to understand the dynamical nature of attractors of iterated function systems. So we're going to call this end result the attractor. We're going to talk about symbolic dynamics later. Let me not get into that. Prove and use the shadowing theorem. It's one of the important theorems in this context for hyperbolic iterated function systems. Interpret the notion of dimension as a power law. This is going to take a while to understand as well. Derive and use formulas to compute and approximate dimensions of attractors of iterated function systems, because the idea is that we're going to be able to associate a number to an attractor like this that acts like a dimension, like you would see in linear algebra. Except that in this case, the dimension of this is going to be a fractional number. It's going to be a rational number, or not necessarily rational, but it's going to be a fractional number. And so the way to think about it is that this notion of a dimension is really about power law, meaning that, maybe I should write it here. So it's related to a power law. And what do I mean by this? The following. If I were to take a one-dimensional thing, let's say an interval, everyone agrees that this has to have dimension 1, okay? If you were to stretch it by a factor of 2, its length, so you make it like this, its length would double, right? So, how should I write this? Let's write it like this. If this is the interval, then the length of twice the interval, stretching by a factor of 2, is 2 times the length of the interval. If I were to do the same thing with a two-dimensional thing, now I want to again say, I want to stretch it by a factor of 2. That means I want to stretch each of these sides by a factor of 2. Because at this point, even when I say I want to stretch it by a factor of 2, you would question, what do you mean by that, right? I mean, let's say that I'm sort of stretching one of these sides. So now, I guess I should say area, the natural sense of volume, right? What is the area of this rectangle stretched by a factor of 2?
In
2 dimensions. It's like, so it becomes like this. 4. And 4 is really 2 to the 2. And really this is C, this is C, this is C, this is C. And this is C to the 1, of course. And this is the dimension, really. Okay? Now, in the case of attractors, you can still talk about stretching, which means that you can still talk about a relation like this. But, you know, the exponent here, which is the power law, turns out to be a weird number. I think, for instance, in this case, it's going to be log 2 or log 3 or something like that. We're going to learn how to compute some examples and so on. So this is an important thing. Yes?
You're referring to an attractor. What is that defined as?
It's this whatever we're left with.
Okay.
Yeah, we're gonna be more specific about what that is, but for that I need to we're gonna have to talk about this thing called the Hausdorff distance. Okay. Use probability measures on attractors. So, and then we're going to sort of start talking about these things from a probabilistic point of view. There's this thing called the chaos game that is sort of slightly related to this, that is like popular. Let me not get into that now. Prove and use Elton ergodic theorem. If you took linear algebra from me last semester, we talked about ergodic theorem in a different context. We talked about von Neumann ergodic theorem. This is a different one. That's for iterated function systems. And that's going to take a while. Okay. Tentative schedule. So basically what I plan is this. For 3 weeks, we're going to study this metric spaces from a general point of view. That's going to be for it's going to be for general purposes. Probably, I think if you take a topology course or something, you would spend more time on these things. But I'm just going to be quick and dirty about this. Like we're going to just do we're just going to cover what we need and then move forward. Then for 2 weeks, we're going to study iterated function systems. Then for 2 weeks, we're going to study topological and symbolic dynamics. Then for 3 weeks, we're going to study dimension theory. We're going to have to formalize all this stuff. And then for 4 weeks, the remaining 4 weeks is going to be about this Elton ergodic theorem and the foundations of probability that we're going to need. Grades. The final letter grades will be determined according to the following weights and cutoffs. So let me just say it. 5% attendance, 35% weekly reports, 40% final report, and 20% presentation. Now, attendance, I'll talk about it later. Okay. We have a couple of books that I'm suggesting. The main book is Barnsley's Fractals Everywhere. That's really a book that is slightly more elementary, probably, for a class like this. But we have like different backgrounds, and I think that would be a good starting point. So if that's your level, perfect. If it's not your level, if you need something more advanced, then we're going to have we can have a look at other more complicated, more sophisticated books. And of course, you know, weekly reports. You decide what you want to put in, and if you know Barnsley is exactly your level, then that's good. There are many exercises in there. You can work on them. If you're beyond that, and if you want to spend more time, you can go for something more advanced. So the level really of this class is also dependent on you. Okay, then there's a book by Petrunen. That's basically for the basics of metric spaces. There's a book by Falconer. It's a standard introduction to fractal geometry for researchers and stuff like that. Especially in the context of dimension, we're going to use this Falconer book, I think. One of the things is that Barnsley's book, even though it has many ideas, some of the proofs are skipped and so on, and I want to sort of supply those. Then there's a book by Pessin and Clement Haga, and it's basically the lecture notes of a similar course that both of them worked on a while ago. So I got my PhD from Penn State, so a lot of the references are from Penn State as well. And I took something about dimension theory, let's say, in grad school from Pessin himself. He's one of the leaders of the area. And Clement Haga Juan is a student. He was a student of him. So I know these people personally. And there's a book by Schroeder. It's like a popular math book, but it has references to many things. So if you're especially interested in sort of applications of these ideas, I think that would be a good place to have a look at. Then there is a set of lecture notes by Rodriguez Hertz and Kurt. Kurt is faculty here. He's my supervisor, and Federica was my PhD advisor. So, okay. Scope. Oh, let me also say this. I think most of these books you can find hard copies, secondhand hard copies, fairly cheaply. But if you can't figure it out, like if you can't find a copy, maybe we can find a digital copy and so on. I'll help you finding the resources. Okay. Scope. Generally speaking, the scope of the course is limited to have citation distance 1 to one of the above resources. So the way I think about it is like this. So imagine all citations, all references, and it's a graph, okay? Each node corresponds to one citation, and that means that if this is one citation, let's say that, let's put it like this. By this I mean both of these citations cite this other guy. So this is time going backwards. So time goes this way. Because you can only cite things that have been published most of the time. But but of course, maybe this guy sort of cites this, and let me put here this. And let's say that this is Barnsley's book. What I'm saying is that, when you're working on something, maybe you don't like Barnsley's book or something like that. You want to study some topic that is covered somewhere else. I'm saying, don't go too crazy. Just look at citations. It's like, okay, this is, if your topic is covered here, that's valid, but maybe Barnsley doesn't refer to this. Okay, then don't use that. It's just that there's a limit, right? Because otherwise you would be able to do just like whatever you want, and that's not exactly, even though I, admire the desire, probably it's not very healthy or efficient, at least at this level. Okay, so that's what I mean by citation distance 1. But of course, if it turns out that you have some other thing that you really want to study, then you can just talk to me and I can say, okay, that's fine. That's related enough. Okay, lectures. Attendance at all lectures is expected. Attendance at random lectures will be taken and will have an effect on the final grades. The number of lectures when attendance will be taken will also be random. So on Canvas, if you had to look at it, there's only A1 under the attendance. So that's I'm saying I'm going to take at least one attendance, and I might take more attendances, in which case you're going to have more assignments that are just going to pop up. And all of this is going to be random. And obviously, this is not something that you should worry about. It's just that I want you to come to all classes, basically, unless there's a major issue. Okay, and I'm recording the lectures. And the lectures will be public as long as I can, but if something happens, it might go down and everything. Okay, weekly reports. Students are required to submit a weekly report each week, totaling 15 weekly reports. Now, if you really think about it and think ahead, I'm going to ask you to submit a report even the weekend of Thanksgiving, okay? So, but earlier that week, you have time. And also, I might drop some of the weekly reports. So you might feel like, that weekend, I really don't want to do this. You can just skip that one. So that doesn't mean that you're not going to get an A. So. But obviously, I'm putting pressure on you to keep working each week on whatever you want to work on. Each week, the report is due by Sunday, by 11:59 on Sunday, ending the week. Late submissions will not be accepted unless you contact the course staff, which is me, with a valid excuse before the deadline. Now, if you've taken a class from me before, you know that I'm very strict about these kind of things. In this class, I'm going to be not as strict, but still I'm going to be strict. So don't do repeated offenses, let's say. A certain number of weekly reports with lowest scores may be dropped at the end of the semester. We're going to talk about the content of these weekly reports later. I mentioned it a little bit, but LaTeX, I'm asking you to write everything on LaTeX, basically, as you're about to submit. Okay. There's some technicalities, again, that you can read. I don't think they're very important at this stage. Final report and presentation. So this is what substitutes a final exam, or basically all exams. So there's a certain schedule. First, I'm going to ask you to declare your topic at the end of week 9. I want the first draft at the end of week 12 for the report. And then at the end of week 13, I'm going to ask you for the first draft of your presentation. Then the final week, we're going to have the presentations, which I'm not going to record, of course. It's going to be only for the attendees. And final report is due by the end of week 15. So basically, this is so that you don't cram everything to the last minute. I'm sort of asking you to sort of start thinking about things way ahead of time and all that stuff. Okay, there are technicalities about this. Let me not talk about that. Exams, no exams. Accessibility, I guess this is important. Let's read it. The University of Utah seeks to provide equal access to its programs, services, and activities for people with disabilities. If you will need accommodations in this class, reasonable prior notice needs to be given to the CDC at this place, and there's a phone number there as well if you need. CDA, sorry, not CDC. CDC is something different. It's the COVID thing. Or MPOX now, it turns out. CDA will work with you and the staff to make arrangements for accommodations. All written information in this course can be made available in an alternative format with prior notification to the CDA. Inclusivity and safety, and this is an important item. Title IX makes it clear that violence and harassment based on sex and gender, which includes sexual orientation and gender identity/expression, is a civil rights offense subject to the same kinds of accountability and the same kinds of support applied to offenses against other protected categories such as race, national origin, color, religion, age, status as a person with a disability, veteran status, or genetic information. If you or someone you know has been harassed or assaulted, you are encouraged to report it to the Title IX coordinator or the Office of the Dean of Students. There are addresses and phone numbers and stuff that you can see there. For support and confidential consultation, contact the Center for Student Wellness at this place, and with this number to report to the police, go to the police. Academic honesty. You are expected to adhere to University of Utah policies regarding academic honesty. This means that ultimately all work you submit must be your own, created without unauthorized assistance, all external resources, including generative tools and computer algebra systems. Obviously, if you're doing something pure mathematical, probably you're not going to use something related to computer algebra systems, but if you want to do some more applied stuff, probably you're going to use it and all that. So all uses must be properly cited and documented within your submissions. Any student who engages in academic dishonesty or who violates the professional and ethical standards may be subject to academic sanctions as per the University of Utah's student code. Generative AI and computer algebra systems. Again, if you've taken a class from me, you know that I take AI very seriously. In this course, you may use generative tools like ChatGPT as well as computer algebra systems such as MATLAB under specific guidelines. These tools are permitted to guide your understanding of topics. The use of generative tools in a submission for LaTeX purposes is allowed, provided that it is acknowledged in the submission. So you want to say something like, I use ChatGPT when typing this thing. for typography purposes, or for other things too, but that's more iffy. Based on my experience, I think ChatGPT is fairly good at helping you type things in LaTeX. Let's say that for some reason your document doesn't compile, it can help you. That has been my experience. Or let's say that you want to sort of render something in your PDF and you don't know how to exactly do it. Instead of searching online, you can ask ChatGPT. It gives some suggestions, some of which work sometimes. Okay, if applicable, you must acknowledge your use of such tools in your submissions. You are responsible for ensuring the validity, accuracy, and relevance of your submissions, whether or not you use these tools. So you cannot be like, there's this exercise, and I went to ChatGPT. That's what ChatGPT told me, and so that's what I put in. So that doesn't quite work. So it's your work. While encouraged, the use of such technology is not required for success in this class. Regret clause: if you commit an unreasonable act, but bring it to the staff's attention within 48 hours of the relevant submission, sanctions may be limited to that submission only, rather than leading to further disciplinary action. This clause will not be applied in the case of repeated violations. Okay, and that's it. Any questions about any of this? So as you can imagine, I'm strict, but fairly open to suggestions and changes and everything. So, yes?
So is your general stance on this whole textbook thing to get the Barnsley one and then acquire others?
Yes. 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 Exactly. Yeah. Any other questions? You're not happy? Okay. Okay. Okay, collectivity. So by this I mean two things: collaboration and competition. So you get to choose what you want to work on for the weekly reports. But what I don't want is everyone submitting basically the same thing. So how to handle this? Well, and so this is this is to simulate a sort of research community. This is like what happens if you're part of a research community, and I'm imagining us to be, this class, to be a part of one research community. And what you do is, obviously, people are sort of interested in similar things, similar problems. That's why there's a research community. So problems are related, but also there's some competition, right? It's like if you're trying to publish something, you cannot publish the thing if someone else already did it, right? And so that's going to require you to communicate with each other. I'll be in communication with you as well, of course, but I'll be more of a referee or advisor or journal editor type of a person, whereas you will be the sort of researchers. In reality, these roles are basically the same. It's just that people rotate. So the editor for one journal is sort of in the researcher position, or contributor position for some other journal and so on. But obviously, we can't do that in this class. And so you don't need to be friendly with each other, but at the very least, you should keep track of what everyone else is working on so that you do different things. And collaboration is fine. Let's say that I started working on an exercise and I'm having trouble figuring it out. And it's like I can, while I'm talking to other people, I can say, so someone else might try to help me, or I might ask help from someone else. That's perfectly valid. It's going to be your submission though, and you're going to have to acknowledge that you got help from this person in your submission. So not acknowledging other people helping you in academia is one of the major, probably the most major offense. And so that's sort of like the idea. Okay, so I realize that this is somewhat not very rigorous, but as we go on, I think we're all gonna understand what exactly do I mean by this, and I'm gonna figure out if this actually works in reality. I thought a lot about what to do about this whole thing, but in reality, in practice, sometimes things don't work, and we would need to adjust and so on. Okay. Any questions about anything? Okay. So the specification documents for the weekly reports are already up. So report 0 is for LaTeX. I'm asking you to put some math stuff in there, but it doesn't need to be syntactic even. Well, it has to be syntactic, I guess. But it doesn't need to be meaningful. I'm asking you to figure out how to, make LaTeX, write an integral or something like that. How do you write a theorem and everything? Very basic stuff. How do you write a matrix? But after this week's report, reports 1 to 14, the remaining 14 out of 15 are going to be math specific. And so the specification document for that is separate. I think we're going to go over that specification document next week. I just wanted to mention a couple of things, go over the specification for this week's report. So I'm not going to spend any time in class about how to do LaTeX and stuff like that. But there's a very nice, so I'm suggesting that you use this platform called Overleaf if you're not using. This is like an online thing, but there's also a local version if you want to download it to your computer and stuff like that. You can use whatever you want, but I suggest especially if you're starting out, to use Overleaf. It's very convenient, I think. And they have like this document, lots of documentation really, and this title has this title, Learn LaTeX in 30 minutes. They just like tell you the basics, and then you're gonna have to learn some more like math stuff on top of that. But it shouldn't take that much time to do this week's report. I wrote down some personal rules that I've developed over the years that might be useful. And in what to submit, I have a couple of commands. So basically, LaTeX is, if you don't know, instead of drawing the integral, let's say, obviously with sort of like with typing, it's not that convenient. What you do is you say \int, and that produces for you an integral. That's the main idea. So it's not a what you see is what you get type of program, which is like a Word, like Microsoft Word. You type what you want, and you say compile, and then you get a PDF file. So let me just write it here. The basic idea is that to do an integral, you do \int. Let's say that you want to do like a 0 to infinity f of x dx. You basically write this, except that here, for this you write \int underscore 0, and then hat infinity. You don't have infinity, of course. You write \infinity. Okay, that's the idea. You basically code everything and then you compile. And this is the industry standard for math and other areas, physics, computer science, all that. And so it's important to know how to use LaTeX. Okay. On Canvas, there's a template source file. These are called tech files that you can use. Okay. Yeah, that's all I wanted to say really about this 0th report. Any questions about anything? Okay. Yes.
When it comes to our weekly reports that are past 0 to 1, is there going to be more of a rigid format for how we format our LaTeX?
Yes.
Okay.
Yes.
Is that in the
Yeah, so we're going to discuss that next week, but basically I'm asking you to produce a report that is 2 to 5 pages long, which doesn't really make sense without specifying the margins and the fonts and stuff like that. And that's what I do in that document when you have a look at it. And then the final report is going to be 5 to 10 pages, I think. I think that's what I wrote in the syllabus. But yes. Okay. Obviously, this is not super rigid, but I just it's a pet peeve of mine to, in classes from my undergrad times, to have like syllabi and like things not being super specific. So this class is not super specific, I realize, but I did the best I could. Let's put it that way. And I feel like it's still a lot better in terms of specificity as to what I'm asking you to do compared to other classes, at least based on my experience. Any other questions? Okay. Yes.
For the first one, or the 0th
Yeah.
we're just kind of, because I looked online, you have this box with a
Yes.
bunch of commands. So
Yes.
are we just supposed to use every single one
Yes.
of them in there?
Yes.
Okay.
Yeah, I'm asking, it's like \author. So if you just write that, if you just copy and paste that, probably it's going to give an error. That's what I'm expecting. But even if it's not, by using, I mean, for instance, like with \author, obviously that's where you put your name. And LaTeX is so that the typography, even though you can adjust it, if you don't do anything, it still prints out a very nice document. And so you can put this \author command somewhere in the document, and it's going to put it in the, or maybe not somewhere in the document, but you understand what I mean. You don't need to worry too much about the spacing and so on. You sort of put the author information as sort of extra information in the document, and then the document system figures out where to put it. It's more automized in a sense. Whereas, for instance, if you're using Microsoft Word, there's no such thing. You just write your name where you want it, and then you have to fiddle around and everything. Yeah, it's that's a. As you're reading through this Learn LaTeX in 30 minutes document, you're gonna sort of see these commands anyway. So it's gonna say, oh, you can use this to do that and so on. There are examples there and so on. So I don't think it's gonna be too complicated, but obviously if there are any issues, I'm happy to help. Okay. Any other questions? Okay. Good. So now we can. Let me think about the timing as well. So we have about half an hour left. Do you think we should take a break, 5 minutes, or continue? Okay. Yeah. 5-minute break. We'll be back in 5 minutes. I have to just add. Okay. Metric spaces. How many of you have seen this abstract perspective about metric spaces? Okay. Good. I think then it's going to be good that we're going to spend basically 3 weeks on the basics of metric spaces. Obviously, it's its own topic. It's very deep, but I should also mention that I'm basically following the Barnsley book. So this is chapter 2, for instance, as I noted in the syllabus. But I must sort of move topics around a little bit, expand on certain things more. In certain cases, give different definitions and so on. So it's going to be sort of up to you to, match what exactly I'm following and everything. So the idea of a metric space is based on what is called the triangular inequality, which says this: if you have a triangle in the plane, the standard plane, flat, then there's a certain relation about the lengths of these sides. Do you know that relation? It's important. It's like Euclid stuff.
It's the total, you take the norm or the absolute value of the vectors added together.
Yeah.
It would be less than the if you were to
Yes. Obviously, Euclid didn't know vectors and stuff like that, but he knew that if you have this length and this length, you're going to get something that is larger than this. That is what is called the triangular inequality. So this is the basic idea, okay? It turns out that because this is such a general idea that there are many metric spaces, and we get to sort of like use certain ideas from metric spaces in many different contexts. So let's start like this. Let X be a set. It's a bunch of things. And let's say that D is a function that takes 2 points in this set, 2 elements, and associates to them a non-negative number. So this is sort of my notation. I'm going to say R like this. This just means that all real numbers, except that it can be at least, it cannot be negative. And so it is like this. And also, in the United States, typically, this is what people write. This is like more British, or more Anglo. I like to use the French notation. It's like pieces of Lego, right? It's like 1, 2. This just means this is closed, this is open. And then if you have 2, 3, they're like Lego pieces, okay? That's the idea. A function. D, E, a function. D is set to satisfy the triangular inequality. If for any 3 points, let me also introduce some logical notations. If, let me write it like this. For all x, y, z in x, I have that this d of x comma z, so the distance between x and z, is dominated by d of x comma y plus d of y comma z. That's a triangular inequality. How many of you have seen this upside down A symbol? Okay, so this is like the logical, this is part of this logical vocabulary. Let me record it here. This means for any or for all. That's the A, okay? Maybe I should write it like that. It's not clear. Let me just write it like that. There's another one, the other way around, E. That's where there exists. So that's that E, okay? There's another E, or epsilon, that I use here that means element of. Okay. Now, typically in a much lower level class, we don't use these things too often, but once you get comfortable with these symbols, you're going to appreciate, because it really allows you to compress information and keep writing things many times. Okay, so that's useful, and I will certainly use these symbols in class as well. Okay, that's a triangular inequality, right? So it basically codifies this idea that the distance from here to there, right, is not more than the sum of the distances from here to there and this distance over here. Okay, that's the idea. Now, this is not exactly a distance, because it turns out people thought about this, and there are certain other properties that you would want a distance to satisfy, but I'll just stipulate that this is the most important thing. The other properties, they are negotiable. I mean, even this property is negotiable, but it's less negotiable. Okay? So, now that we have this, so that's what I want you to keep in mind. This is the big thing. This is the important thing. And if you see an exercise that says, here's a set, here's a d function, show that it is a distance, probably, even though it has other properties that you probably need to check, this is going to be the slightly harder one. Okay. D is said to be a distance function or metric or metric for short, or if a couple things, so I think 3. So 1, 2, 3. So it has to satisfy the triangular inequality. Second, or maybe I should ask you, what should be a second property? Yes?
If two things are the same thing, there's no difference between them.
Exactly, right? Obviously, the distance of a point to itself should be 0. But more, really, I want something slightly more. So let me write it like this. Okay, let me be rigorous. For all x and y and x, the distance between these 2 points, x and y, is 0 if and only if, so it goes both ways, x is equal to y. Right? So that means that the distance of a point to itself should be 0. And if 2 points have 0 distance, they literally they have to be the same points. Okay, so this is the separation axiom, is I think what people say. And I'm not going to be super specific about writing these logical quantifiers at each step. Eventually, I'm just going to stop writing these. Okay, it's clear that it's for all x and y, because otherwise it takes time. And then the third one, any ideas for any suggestions for the third? Going forward, I'm not going to be as I'm not going to ask that many things, but let's start slow. What should be a third property, you think?
Distance between x and y is the same as the distance between y and x.
Exactly, right? So this is a symmetry property. So the distance, right? So it shouldn't matter when it comes to the length of this line segment, whether or not you're sort of looking at this or this way. Now it turns out that in some situations you don't really want this. The typical example people give is that you have sort of like a mountain, and you're here and you're there. If we're using this definition, this is that distance. But obviously, if you have any experience, going from here to there is not the same as going from here to there, right? Like going up has different, I mean, people say that going up is harder, but I feel like going down is harder, but it depends on how you think. So that's why I'm saying these are questionable, but almost always you want to have something like a triangular inequality. And even if you have a function, d, that has this triangular inequality satisfied, you may sort of like do certain constructions to obtain these properties. But if you don't have the triangular inequality, you really don't have it. Okay? Maybe you have something else for it instead of it, but you don't have Ti. Okay, any questions about this? Okay, examples. Of course, the plane, right? Examples. But let's start even simpler. Oh, okay. Before examples, let me just add one more definition. Of course, a pair xd, where x is a set and d is a distance function or metric on it, is a metric space. That's the definition. Okay. So you have a bunch of things, and you also have a notion of distance that you can use to talk about distances between points in that. So that's the definition. Examples. And let me just write it like this. So I have two dots here. Takes two inputs. That looks like a face too, but takes two inputs, two numbers. You subtract them, take the absolute value. I'm saying that this is a distance. I'm not going to verify, but it could be an exercise. Okay. Of course, more generally, if I have Rn with a standard norm, it's a distance. So in this case, so maybe I should write it. That's what I'm saying. That's a distance. And here, so x minus y in norm, because we're in Rn now. So these are vectors really. This is the sum of all entries, xi minus yi in absolute value squared, and then squared 1 over 2. So this is the standard Euclidean distance. Okay, here's another one. This is really a generalization of this. What you can do is you can change this number here. You take a number that is at least 1, not infinity, then you can do the same thing. I'm going to write sub p. And the definition is exactly like this, except that instead of 2, you have a p. Absolute value to the p, right? Inside the summation, you have the exponent, and then you sum everything, and then you take the 1 over pth power. Which tells you that given any set, in this case Rn, there are possibly many distances. So this is what is called the LP distance. LP norm or LP distance. LP distance. Okay? Yes?
You know what the L stands for?
Probably Lebesgue. So we're going to spend quite a while toward the end of this class, but there is a theory of integration that is more robust, let's say, compared to what you guys learned in calculus, which is Riemann integration. There's this other guy called Lebesgue, and he came up with a different type of integral that works the same if Riemann integrals work, but it works in other cases when Riemann integrals may not work. So that's good. And there's this uppercase LP spaces, lowercase LP spaces. I think this is sort of like a notation. It's not super important, but p distance you can call it too. But yeah, it's named after someone. Okay. Now, so these two metric spaces, I'm leaving them to you to verify. So that's an exercise that you might do for week 1 perhaps. You may want to do it, you may want to do some of them. So these are different spaces. But it turns out that they are, in a sense, equivalents. Okay? They are basically isomorphic. They are the same in a certain sense. We're going to learn about that later. But for now, these are different examples. Maybe I should mention also, because when I first saw this, I didn't quite understand why people would even look at this. It's like, why are you generalizing this? It turns out that, so metrics are about measuring things. And it turns out that if you use sort of like a different number than 2, it emphasizes different properties. So it's about how spread out certain things are. I'm just going to leave it at that, but there's a reason why people look at this p. In this spectrum of exponents, you can also, in fact, use infinity. Okay? But that's, so what does it mean to take the infinity power of something? It's not super clear, but at the very least I can do this. So let me just write L infinity here. So what is this L infinity? So d infinity, by this I mean this guy, x and y. Does anyone know how this is defined?
The maximum.
That turns out to be another distance. It's also, again, equivalent to each one of these p's. Here's an exercise. So, okay, let me say it like this. So one way to make sense of this infinity is, of course, to realize that, okay, it should be a limit. And that indeed turns out to be true. If you were to take the limit as p goes to infinity, you get this exercise. Okay. So you take two vectors in Rn, you look at the p norm, or p distance between them, it's this number. You take this expression, it's a function of p for fixed x and y. Take the limit as p goes to infinity, it's single variable calculus at this stage, because this is a number. I'm saying this number converges to this number. Okay, that's an exercise. That's a nice exercise. Okay, any questions about these? So Rn, so typically we're going to, in this class, we're going to focus on this. But there are more sophisticated examples that we're going to have to use. That's why I'm sort of trying to cover this as generally as possible within reasonability. Okay. Here's another important example for us. Shift spaces. Four, five. Shift spaces. This is something that we're going to use, especially in the context of what people call symbolic dynamics. And so now the set X is the set of words or infinite sequences. Let's say it like that. So let me write it like this. X bullet, I'm going to write. Let's write it like this. It's a set of all functions from non-negative integers. Z stands for integer. Taking values in, let's say, in the set A. So this is a set of all functions from this to that. Okay, what is A? A is going to be a set of alphabet, or it's going to be the set of the set that is the alphabet. Let's say that my symbols are 0 or 1. Okay, so you can imagine any point in the set as sort of like a ticker tape, is what people say. So if I take an X, a point in capital X, X I can imagine like this. So it's a strip, okay, and I have the 0 entry. It's some number, either 0 or 1. I'm writing it like this to denote that this is the 0 entry. This is, from a dynamical point of view, this is what I see today. Now, tomorrow I see this, x1, then I see x2, and so on. Okay? And this is called the ticker tape. The idea is that you imagine that this is sort of like these numbers are values of stock of one stock, and there's a machine that at each step sort of pushes out one thing. And so that's why, Wall Street and everything. This is called the ticker tape. You can imagine there are other representations. So this is a one-sided shift space. You can also think about two-sided ones. It's not that important, or it is important, but the difference is not that important. Let's say y is like this. All functions from integers, all integers, negative included, into the alphabet. And a point here in this space, lowercase y, really is basically the same thing, except that instead of running off to infinity in one direction, it runs off to infinity in the negative direction also. And that's why it's important to denote somehow where the 0 coordinate is. So you know the future, or past, depending on how you're looking at, and then you know the past. Okay? So this is just a set. I'm running out of time. Here's a distance for it. The idea is that, at least for our situation, for our case, you want to define a distance on this set in such a way that it becomes reasonable to think of this as the binary expansion of a number. That's the idea. So you can say, for instance, distance between 2 points in the first guy. Let's write it. Okay, I wrote it like this, but I really mean here for all. Okay, I'm going to be vague about this. Well, if this is a decimal or binary expansion or whatever, it must be the case that this entry matters more in terms of distances. So what you can do is this. You can take an infinite sum. N from 0 to infinity, xi minus yi in absolute value. Divided by, of course, this doesn't converge necessarily, divided by this, 1 over 2 to the I. So now, you see, I'm emphasizing the earlier coordinates or the discrepancies between the earlier coordinates more. And as I run to the future between these two symbols, or ticker tapes, I'm emphasizing it less and less. Because this, as you know, goes to 0. Okay. I think I have 1 minute, but I think it's a good place to stop now, unless there are any questions. Yes.
Okay, so the first question was on the notation for the like real to the end. Was that dimensional? Or
Yes,
okay.
that was a dimension.
Okay, and then the second question I have about this whole tinker type thing, the distance between them is each one of these is somehow related with alphabet, right? How does that
Yes.
explain the subtraction and distance between them?
Yes. I mean, in this case, okay, fair enough. But in this case, what I mean is that this is 1 if they're not the same, and they're 0 if they are the same.
Okay.
Yeah. This is what is called the discrete distance. Next time I'll mention that then. It's a good point. There's something called the discrete distance. That distance is that discrete distance. Good.
And I guess along those same lines, how do you hard or rigorously define what the alphabet is here in this case?
I mean, I can just...
Not necessarily in this case, but what is it more generally besides just
Any
0?
set.
Any set? Okay.
Yes. Because any set you can define on any set a distance.
Mhm.
So, yeah. Yeah. Okay. Good. Thank you. I'll see you on Thursday. Hello again. So today we're going to look at more examples of metric spaces. Then I'd like to discuss functions a little bit more. Their continuity and other important properties that we're going to be using in this class. So first of all, last time we were discussing this shift space business. So I wanted to slow down a little bit and give more definitions here and more examples. First example is this. I can take any set X and I can define a D function between 2 points, X and Y, in X, like this. Right? So I would say that D of X comma Y is 1 if they are different, and it is 0 if they are the same. So this is what is called the discrete distance. Discrete distance. Here's another example. I can take it again, any set, X whatsoever, and I can just say, okay, the distance between 2 points is 0. Okay, that's another example. Gotcha. This is not a distance, right? Because in general, because if you have 5 points, let's say, I'm saying that the distance between any 2 points is 0. But for a distance, remember one of the properties was that if you have different points, the distance has to be positive. So this is not exactly a distance. It's called the indiscrete pseudo distance. It's almost a distance. Clearly it satisfies a triangular inequality, but it doesn't separate points. But when you have a set together with a distance function, you should really sort of try to imagine how it would look like geometrically. So if I have, let's say, the reals, so think of X as the reals, the whole line we would like to imagine. But as you can see, if I were to think of X together with the discrete distance, what happens is that you don't anymore have this line. All of these points are dispersed in space. Somehow, no matter how close 2 points seem in sort of standard, what we would call topology, relative to this distance, the distance between 2 points, no matter which 2 points you choose, is going to be 1. So imagine, so in space you just blow up the whole real line and there's no structure whatsoever left. And here, if I were to switch over to this guy, now what I do is I take the real line and somehow I crumple all of them into 1 point. Okay, so the topology, the proximity, the notion of proximity between 2 points of the real line changes, but still it's a perfectly valid object mathematically speaking. And indeed you can sort of interpolate these two, or any distance whatsoever if you want. And you can think about, so here's a 4/5 example. You take any distance, any metric space whatsoever, and then scale that D by whatever number you want. Let's say goes to, so instead of that, I can look at x comma lambda d. Now I have a metric space. I know where points are. And then as I vary lambda, let's say that I take lambda to be 15, from 1 to 15. So points sort of like, grow apart. It's the same shape, same broad shape, let's say, same coarse structure, what people would say, but they're, getting far away from each other. Or, if I wanted, I could take lambda smaller and smaller, and I could shrink it to 0, in which case all of the points, whatever structure I have, everything would shrink to 0. Okay. So, third example, this family of examples, shift spaces. I take an alphabet, which, like we discussed last time, is just a set, but for us it's going to be finite. It's going to be a finite set, and typically people just use integers 1 to n, or 0 to n minus 1, whatever you want to call it. And my sigma, the capital sigma, is going to be the shift space, and it's a set of all functions from integers to this set, which means that it's basically, so any element here is a bi-infinite sequence. Now I can take a theta, a number that is larger than 1, then for any two sequences, omega and eta, I can define this distance. D sub theta between omega and eta is this infinite sum. So the sum goes to positive infinity and negative infinity. And I want this to converge, and that's why I have n in absolute value. So if you want to write this down, you would have 1 over theta to the 0, 1, 2, 3, and so on, and likewise for negative time. And then what do? I look at the distance between these two symbols. So the nth symbol that I see in the omega sequence, I compare that value. Okay, so maybe I should use m there, actually. Okay, it's a different number. So here, omega n is a number between 1 and m, and so is eta n. And I'm saying, okay, I'm going to use a discrete distance here. So I'm thinking about whether or not these two symbols are the same or not. And it turns out that this is a distance. Now, it's an interesting question. What happens when you change this theta? It's slightly technical, though, at this stage. I think what I'm going to do is I'm going to write some notes about certain technical matters, which will possibly include exercises as well. And eventually, I'll upload them on Canvas. But for now, let's just leave it at that. Here's another important example that you might need in this class, especially if you're interested in interpolation and stuff like that. Many function spaces you can think of as metric spaces. So here's a function space. This is my notation for the space of all continuous functions from the unit interval that takes real values. And I want to figure out what is the distance between them. Has any of you have an idea as to how I can define this? There are many ways of defining this, of course. I can say I'm going to take the discrete distance, but I want to define something more natural. Yeah.
Take the maximum difference between the function over its domain.
Yeah. So this. This turns out to be a very nice natural distance. And so let's think about what this actually means. So I have two functions. I'm thinking of the functions as points, but also we know that you can draw the graph of a function. So what you do is this. So I'm trying to imagine what it would mean for two functions to be close relative to this distance. So this is, let's say, 0 to 1. And I have one function here, which is f. I want to figure out what it means for some other function g to be epsilon close, or epsilon close to f. Well, the idea is this. Of course, G2 has a graph, right? But I want to do the following. I'm going to compare the values of f and g for the same input value, which means that I'm looking at this spread, if you want, vertical spread. And really what I'm doing is this. I'm taking sort of the tube or strip around the graph of f, such that this distance, so this length, is epsilon. It is epsilon everywhere, okay? And it's epsilon here as well. So if this is f of t, this is f of t plus epsilon, and this is f of t minus epsilon. So what I'm saying is that in order for g to be epsilon close to f with respect to this metric, it must be the case then that its graph is inside this strip. I don't know exactly where. Maybe it gets very close. But it doesn't go farther. That's what I'm saying. Okay. That's one way of thinking about this. Okay. Any questions about these examples? There are many more examples in the textbook and other places, but these are sort of the most fundamental ones. Yes?
So for the example 5 here, are we assuming the x comma d is already a metric space?
Yes.
Okay.
Yes. Any other questions? Okay, so an important thing, of course, is this idea of a metric subspace. If I have a metric space, I can take a subset of it, and that subset too is a metric space in and of itself. Metric subspaces XT metric, and then I take a subset A. So this is my notation for a subset. It's a region in X. Then I can define D sub A, let's say. Well, this is nothing but, so if I were to take 2 points in A, well, what is this distance? Well, if I take 2 points in A, they are also in X. That's what it means for A to be inside X. Okay, so if this is my X, I'm saying, I can do this. It doesn't need to be connected, of course. So maybe A has like multiple components. And I want to figure out the distance here. Well, I can just look at this distance. It doesn't need to necessarily stay in A, is the point. And this is nothing but D of AB. In which case, I would call this pair A comma D sub A, which in and of itself is a metric space, after all, a metric subspace of the bigger space XD. And so, for instance, in this case, the interval 0 to 1 is a metric subspace of the real line, right? How do you figure out the distance between two numbers not more than 1 and not less than 0? Well, they're just numbers. So just look at the standard distance between them. Okay. Any questions about this? Okay. Now that we have the basics, there are other constructions that we can discuss about metric spaces, but I think this much is enough. Let's switch over to continuity. So now we have a sense of what it means for 2 points to be close to each other. Next up, if you think about your calculus classes, eventually we should, I guess in calculus you don't discuss these things, but next thing we want to discuss is continuity. And in fact, I'm going to do something, I'm going to cover it in a slightly different fashion because that's how they cover it in the book, and maybe it's good. So I'm going to talk about certain properties that functions might have, functions defined between metric spaces. Continuity and further Lipschitz properties. So from now on, I'm not going to keep saying this is a metric space, blah, blah, blah. If I just write a capital letter X, that's a metric space. I'm not even going to mention or write down the distance. So I take a function from X to Y. Both of them are metric spaces. So X has its own metric, Y has its own metric. And let me take a theta, positive number. Then f is set to satisfy the theta-Hölder property, or it satisfies the theta-Hölder condition. If there is a number C, positive, such that for any 2 points, x1 and x2 in capital X, I have the following inequality. So I take 2 points in X, apply F to them. Now I have 2 points in Y. And then I measure the distance between them. I want this to be dominated by C times this. C times the distance, the original distance between the 2 points, to the power theta. Now when you first see this kind of a condition, it looks bizarre a little bit, and I realize that. After I go through the definitions, I'm going to try to give some intuition as to why this will be useful. So this is question.
Oh, no, I was just
Okay.
that.
So one Hölder, meaning that if you don't have an exponent, that's called a Lipschitz function. Okay. In other words, if f satisfies the one Hölder condition, you also say simply it satisfies the Lipschitz condition. If f satisfies the Lipschitz condition with this number c less than 1, then it's called a contraction. If it is Lipschitz with c less than 1. But this, I hope, starts to make sense because, so let's perhaps write it down explicitly. So let's say 1 over 2, right? Like maybe my C is that number. something like that. Well, why would I call it a contraction? Well, that's because I take 2 points, apply f to them, and somehow the images are closer compared to what I started with. Okay? So that's why I'm thinking about this. I realize that these still don't make that much sense, but at least this should be reasonable. F is called distance preserving if instead of inequality, you have equality, and C is 1. That's also straightforward, I think. It literally preserves distances, right? So if and as you can see, here I wrote the subscripts x and y to represent that, oh, this is a distance of x, and this is the distance of y, but I didn't write them here because I was lazy. So at some point, you stop sort of writing things down. But that's what is meant, right? I'm literally saying here that the distance between any 2 points x and y is preserved under when I apply f to it. Okay? So these are some definitions. If f is distance preserving, and furthermore, it has a functional inverse, right? It is an invertible function, then you call it an isometry. Same metry, same distance. It's an isometry if distance preserving and invertible. Has an inverse, or in other words, it's a bijection. Okay? So let's perhaps give examples. Let's start with the isometry case. Well, obviously, identity, right? X goes to itself. If I'm using the same distance, it should be an isometry. X is invertible. You can use itself. It inverses itself. But let's think about like linear maps. Let's say that I have 2 Euclidean spaces. And with the standard Euclidean distance, right? What is called the L2 norm, what we called last time. So let's say that I have here, let me write it like this. Q, a function goes from Rn to Rm, isometry. Can you tell me anything about this Q? So it's isometry and linear. Okay, sorry. Can you tell me anything about this Q? What is a linear transformation that also preserves distances?
It'd be an n by n matrix of determinant 1.
Okay, so first of all, I mean, that's one example. You're true. You're right. So first of all, we should think about whether or not these 2 dimensions have to be the same or not. Well, by definition, an isometry means invertible, and we know from linear algebra, invertible means determinant has to be non-zero at the very least. Okay, which means that in particular, these dimensions have to be the same. First of all, okay. So it's it's a square matrix. Okay, so it's a square matrix first of all. Let's say that n and m are both 2. So what's a linear transformation from the plane to itself that preserves distances? Yeah.
Do the reflection matrix like 0, 1, 1, 0.
We can do reflection, or there's a much larger family, which is a rotation, right? Okay. In general, it's going to be an orthogonal matrix. You see, this is kind of interesting because if I didn't put here this condition linear, you wouldn't be able to go over there. And when you think about this, isometry is about preserving distances. Orthogonality is more about preserving angles. You get something more out of linearity. So it's important. So you can think about rotations or, like your colleague said, reflections and so on. So that's one example. We're going to discuss things like this more later. Okay, so now let's go to single variable calculus stuff. So a function I'm going to define from the interval to the real line. I want something that is theta Hölder. So let's say 1/2 Hölder. Well, it turns out that the standard example for this is this. X to the theta. Here's this is an exercise for you. Furthermore, this function is not Hölder with respect to any larger exponent. Not, let's say, theta prime Hölder for any theta prime larger than theta. So somehow this is sort of like the best you can get. So when it comes to Hölder functions, that means that, or you should think about it like this. You want to have as large an exponent as possible. In particular, if you can, instead of doing Hölder, if you have Lipschitz property, that's the best you can have, or you want to have. So how does this look? It's between 0 and 1. If theta were 1, I would have the diagonal line. If theta were less than 1, let's say x squared. Hang on. So I want to say, hang on. I want to say theta is between 0 and 1 here. If theta were more than 1, let's say 2, x squared, it would be under, right? This would be x squared. And if I were to have x to the 1 over 2, it would be over. So it looks like this. Okay, so this is sort of what you should think about. Now that means that, and the important point here is the 0. Okay, so if I have a theta Hölder function with theta between 0 and 1, so that it's, I guess, concave, that means that you see, this allows you to have slope. So you're losing control about the slope of the graph of the function around the origin. That's what you should think about. So really, Hölder property or Lipschitz property is about controlling the slope. It's related to differentiability, but as you can imagine, in this general setting of metric spaces, what it means for a function to be differentiable, it's questionable, but at the very least, these inequalities make perfect sense. Okay. Here's another example, or exercise rather. Now I said these theta Hölder conditions, or Lipschitz property, they're all about controlling the slopes. And especially, or at least in the context of single variable calculus, let's say, when you're talking about slopes, something else should come to your mind. What are slopes about?
Or change.
Yes, the derivatives, right? So exercise, proposition, let me prove this. I'm going to take a function like this, and I would like it to be continuously differentiable. What does this mean? This means that it is differentiable. So f prime, this other function, exists for any point x. And further, f prime is a continuous function in and of itself. So i.e., and is continuous. Okay? Now, I claim that any such function is Lipschitz. Then f is Lipschitz. Any ideas as to how I can do this? So, and in this class we're going to do some proofs. So what do I want? I want to prove that f satisfies a certain inequality. And instead of writing d and stuff like that, in this case, we're in the context of single variable calculus. We might as well use absolute values because that's what I'm using, really. So what I want is this. So distance between f of x and f of y is dominated by some number times x minus y. And this inequality should remind you of something. Not quite. It's a theorem that you used in single variable. Yes?
Are we aiming for triangle inequality?
No.
Okay.
This is the inequality. But it's something that, it's a theorem in single variable calculus that something like this happens.
Average value?
Almost.
Mean value.
Exactly, right? So mean value theorem says, we're going to have to work with that a little bit, but maybe I should remind you, mean value theorem says that if you have any 2 points, right, because if I were to take this to the other side as a denominator, that's the rise over run business. This says that if I were to take any 2 points, there's a point in between, okay? There's a z between x and y. Here I'm assuming that x is less than y, but it's the same thing, of course, such that this rise over run is exactly the derivative of f at that point. That's what the mean value theorem says, right? I mean, this is one of the reincarnations, let's say. Okay. Now the problem here is that we're not done because somehow this z that I chose over here depends on x and y. But x and y are variable, so I need to figure something out about that. Well, what you can do here is this. I know that, this f prime function, by definition, by hypothesis, is itself continuous. So f prime has a maximum and minimum on 0 and 1, because that's one of the nature, it's part of the nature of being a continuous function on a closed interval. Okay? Because it has to start somewhere, right? So let's say this is 0 and 1. it's going to start somewhere, and it's going to end up somewhere, and you cannot sort of lift your chalk or you lift your pen to draw the graph, which means that eventually it's going to have a maximum and a minimum. Okay? So with this idea, you can get rid of this. Let's call it M, let's call it C. Then for any x and y, I can get rid of this quantifier in the middle, because I could say, I don't really care that much about what that value exactly is. Let me just say, as long as I can bound it from above, it's fine. So let me perhaps write it like this. F prime of z subscript x and y. This point depends on x and y, but C, this capital C, doesn't. Okay? Take this to the other side. And you have this. So it's a parenthesis, but you can basically turn it into an absolute value in this case. Okay? And that's the end. I was able to show that any continuously differentiable function on the unit interval is in fact Lipschitz. Okay? Any questions about this?
Can I just verify notationally?
Yes.
Are your backwards brackets open boundaries?
Open, yes. Open bracket, yeah. Because it has to be, I mean, that's sort of like the beauty, right? Like you get to find a point in between. Yes?
In elevator pitch, is
Yes.
there a reason the US doesn't use this as often? Because it's much more intuitive.
Yeah, I mean, yeah. It's, I mean, you know, it's
the US.
It's fashionable to, you know, not like the French.
Oh, yeah,
So,
that's right.
I mean, that's a historical question. Probably that's like someone's PhD thesis.
Yeah.
But,
why is it fashionable?
Yeah. But, yeah. Anyway, so that's that. Now, exercise, the same thing holds if you have a multivariable function taking real values. There's again a mean value theorem. It's not exactly this. It's slightly more complicated, but it does do the same thing. So that's an exercise. Okay. C1. I'm just going to write C1 instead of continuously differentiable. I'm saying this is differentiable once. That's sort of the notation. C1 implies Lipschitz. Okay. Let's think about the other way around. If I were to have a single variable function like this, and if it were Lipschitz, can I say that it is also continuously differentiable? So are these two things the same things? Probably not, because otherwise I wouldn't have defined it. And indeed, this turns out to be an important thing. It's a big theorem. I think if you haven't seen this, studying the proof of it might be useful. And therefore, I'm going to leave it as an exercise. This is a very fruitful idea. So exercise. This is called the Rademacher Theorem. If from 0 to 1 to R is Lipschitz, then I would like to say that it is continuously differentiable, so that it's a true inverse or true converse to this proposition that we discussed. It turns out that that is not true, but the next best thing is true. Then it is differentiable and now I'm going to introduce some further terminology that's going to come in handy in this class. Differentiable, Lebesgue almost everywhere. Okay. Now, what does this mean? Lebesgue is the same guy that we were discussing, the person who came up with this different way of integrating things. And here I'm saying essentially that, okay, that the following. So I want to say this. Take all those points such that f is not differentiable there. So f prime does not exist. Okay, that's a subset of the interval. What does this mean? It means that, okay, so f prime of x, we say that it exists if a certain limit holds, blah, blah, blah. I'm saying that that limit doesn't converge, okay? So this, I'm saying, is negligible, is negligible. Okay, what does that mean? Here's a definition. Or negligible, or another way of saying this is it has Lebesgue measure 0. That's a more accurate way of saying this. Has Lebesgue measure 0. Let me just give the definition. A subset, let's do this in Rn. So that's an important definition. So for now, I'm going to give the definition as an atom. So each of these words has its own meaning. But for now, we're just going to learn what it means to say, for a set to have Lebesgue measure 0 without really knowing what each of these words mean. But a subset of Rn has Lebesgue measure 0 if okay, even before that, maybe I should say something about this. So I'm saying that its size is 0, and if you're thinking about these kind of things algebraically, something is 0 if it's 0. Like there's no sort of bargaining about that or bartering. But if you're doing analysis, if you're doing calculus, you have that something is 0 if it's less than any other thing, right? That's sort of like the principle. So this is, I think, what Turnstile calls the n epsilon of room business. And principle. That says that maybe I should write it more generally. So in a metric space, X, 2 points are the same if and only if for any epsilon positive, their distance is less than epsilon. Okay, if you can do this for any epsilon, that means that those 2 points are the same. Because there's no positive or non-negative number that is less than any epsilon using our standard numbers, let's say. There are other formalisms where this doesn't exactly hold, but for us, it does hold. Okay, this makes sense, of course. And so what does this mean then? It means that that set has a Lebesgue measure less than epsilon for any epsilon. So now I need to formulate that, and then after I formulate it, maybe we can take a break. If for any epsilon, there are countably many rectangles, infinitely many, right? But how many of you have seen this word countable? Okay, infinitely many. I don't want to say infinitely many. I'm going to say countably many. It basically means the same thing, except that infinite means something more general. Or cubes, or whatever you want to call it. Boxes. And what is the point here? The point is that I get to enumerate these boxes that I have using integers, not real numbers. So it turns out that real numbers they're still infinitely many real numbers, but there are significantly more real numbers compared to integers, it turns out. Such that using these boxes, I get to cover A. So I'm taking the union like this and this. If I were to take, so the volume, if I were to take the volumes of each of these boxes and add them up, this is not more than epsilon. So that means that I get to cover A using a bunch of boxes. I don't care how many really. It's just that I want them to be small. That's the idea. Now probably, like this is an advanced exercise, let's say, or even if you want to learn it, it's like you can sort of read from a textbook the proof of this, and sort of as part of your one of your reports, it could be sort of a sort of detailed exploration or exposition of this theorem. And indeed, this theorem is true in higher dimensions as well. And in fact, it's true even more generally, because as you can imagine, this basically says that if you have a function that is Lipschitz, it's basically differentiable. Now for general metric spaces, differentiability is questionable, but we can talk about Lipschitzness, which means that insofar as there's a Rademacher theorem for whatever metric space you're looking at, then you can really start talking about differentiability in calculus and stuff. So you see, this is very powerful in that regard. A big name around this is Pierre Pansu. Okay, I'm going to give 3 names actually. So, Pansu, Mostow, Margulis. Just follow these names if you want to see how far you can take this. Okay, good. Any questions about this? Okay, 5-minute break. Okay, let's get back. Okay, let's continue. So here are 2 exercises that are related. The standard Cantor set, the thing that is the leftover, right? You start with the interval, get rid of the middle thirds, and so on. That has measure 0. Okay, that's a much easier exercise because you can think of it like this, right? You can say, oh, in order for the Cantor set, the remainder to have measure 0, everything else should have measure 1. It should be everything else. So let me write it like this, perhaps. If you have an interval, if your set is an interval, its Lebesgue measure is literally the distance. Okay? So somehow this Lebesgue measure, at least in one dimension, gives you length if your set is nice. But for our purposes, sets are not going to be nice. This is still going to work. Okay? That's the idea. So how can you do this? You can just figure out how many, you can figure out the total length of all the intervals that you're getting rid of. You're going to realize that that adds up to 1, which means that you're basically getting rid of all measure, and what you're left with has measure 0. It's there, but it has measure 0. Another exercise that is important is that even though it has measure 0, it has infinitely many points left in it. Okay? So that's sort of like a paradoxical thing, but it is true. So these are two different senses. How many points does a set have, or what is its measure? These are two different senses in which you can talk about the size of a set. And it turns out that based on what type of a notion that you're using, you get different answers. And in fact, later on, when we start talking about dimension theory, we're going to talk about something called Hausdorff measure, or Hausdorff dimension, which basically interpolates between these two ideas. Okay? So here's a preview. So preview. There's something else. It's another measure. It's not measure of Lebesgue. It's measure of Hausdorff, some other person. Measure interpolates the two, Lebesgue measure, and the number of points of a set is called the cardinality. And cardinality. Another name for it is going to be counting measure. Counts how many things there are in something. So here's the idea. You take your set. Let's say it's in R. This is going to turn out to have dimension 1. It's in the sense of linear algebra, but if it works in linear algebra, any other dimension probably is going to give you the same definition, same number. So this is going to have dimension 1. A might have dimension 1, dimension 0. So here, okay. So in this graph, the horizontal axis is a dimension. Different dimensions correspond to different x points. So this is a dimension. And the vertical axis corresponds to the measure. Okay? So this means that if I look at this point represents having this measure relative to this dimensional something measure. That is going to be the Hausdorff measure over there. So what happens is this. So let's say that this is 1, and I'm going to need to have infinite measure 2, because I'm saying it has infinitely many points. That means that relative to counting measure, it has infinitely many points. So here's infinity. So here, you start at infinity, and somehow you're sort of changing the notion of dimension. We haven't discussed this, but Hausdorff measure exactly does this. It's a family of measures, really. As you're changing your parameter from 0 to 1, you know that you start at infinity after this exercise. And you know that if you come over here, you're at 0. So what happens then, we're going to learn, is that there's a critical point here, critical x value, which is the actual dimension of the set that you're looking at, where there's a drop-off. It's almost like a phase transition, okay? And whatever number you get, if you use the appropriate dimension, is going to be the Hausdorff, the actual Hausdorff measure for the thing. We're going to discuss this more, but for now, let's just say that this is going to be the true, let's say, Hausdorff dimension. We're going to spend quite a while on this idea, And again, what does it mean? This is a true Hausdorff dimension. It's saying something about the power law, the exponent in the power law, if you just focus on that set. Okay? This is going to take a while for us, and it really is one of the sort of pillars of this class. Okay? Just wanted to mention this. Okay. Any questions about these things? Yes?
When you use interpolates in this context, are you saying that like it's in between, between the Lebesgue measure and the cardinality?
Yes.
You're saying that the value that comes out of the Hausdorff measure is into
Yeah. I mean, what I'm trying to say is the following. Okay, so there's going to be, so this Hausdorff measure is really a family of measures. So this is going to be the S-dimensional Hausdorff measure. It's a family. S is a real number. S varies here. Okay? I'm saying h to the 0 is cardinality, h to the 1 is Lebesgue, h to the 2 is two-dimensional volume area, and so on. So length. Okay, and this is where it varies. Okay. Yeah. Okay, any other questions? Yes?
So just to double check, what are you referring to when you're talking about the dimensionality here on this?
Okay, so I would like to imagine this, right? So the standard notion of volume in dimension 1 is length. And the same thing in dimension 2 is area. In dimension 3 it is volume. And if I were to take a three-dimensional space, and if I were to take a curve in it, I would say that it has dimension 0, right? Because it's a zero, because you have to have like 3 dimensions.
Yeah.
So dimensionality in this sense allows you to talk more specifically about things. Because like a curve in three-dimensional space has 0 volume, but it has length. Okay, so that's the idea. Okay? Any other questions? Yes?
So, putting this into the context of the Cantor set to try and get a little bit of a better physical read on it.
Yes.
So when you cut up that line,
Yes.
interval in the Cantor set, so we can kind of think of it as slicing and taking something out every time.
Yes.
And as it gets farther and farther along, those leftovers start to look like individual points instead of
Yes.
intervals. We're trying to get to the critical time where that switches between.
Not quite, not exactly, because you go all the way down.
Okay.
The point is that you want to again think about dimension in terms of power laws. So you want to say, okay, so if I were to take sort of like an interval, and interval inside the 0, 1, it intersects with the Cantor set, let's say,
Yes.
and you start growing that interval. You want to figure out how many more points you're getting inside the Cantor set.
Okay.
So that's my power law.
Okay.
So it's going to give a fractional value. And it's going to turn out that in this case it is this number log 2 over log 3, turns out. So here it's going to be this. It's going to be it's a number between 0 and 1. So we're going to say that the Cantor set, the way we defined last time, has dimension this. We're going to spend more time on all of this. Yeah, this is just a preview. Yeah. Any other questions? Okay. Okay, maybe I should also say why you should expect something like this. In the denominator, so it's going to be log over log. Where are these numbers coming from? 2 comes from the fact that you're splitting the thing into 2. 3 comes from the fact that at each step you're shrinking by a factor of 3. Okay? Iterated function systems is essentially useful because there are formulas like this for iterated function systems, or rather sets that are attractors to nice iterated function systems. Okay? That's the idea, yeah.
So it's iterative?
Yes.
Okay.
Yes. Yes. Okay. Now, if you believe what I said, you can also compute the dimension of this Sierpinski business. It's the same idea after all. That's an exercise. Now that I've mentioned it, maybe I should write it here. If this is true, then compute the dimension of this guy. Okay. So let's go back to what we were supposed to cover. So I should have a look at how much time I have left. Okay, 13 minutes. Okay, I'm going to give some more definitions. Okay. Last time we discussed something I sort of mentioned, this idea of two distances or two metrics being equivalent to each other. So this is one way they can be equivalent. Let X be a set, D1, D2 be two distance functions, two metrics on X. In the textbook, they call it equivalent. I'm just going to use something more specific. I'm going to call them Lipschitz equivalent. They are Lipschitz equivalent Lipschitz equivalent if there are numbers, there's one number positive such that for any 2 points I have sort of like a sandwich relation. So C times d2 of xy, and from the other side 1 over C times d2 of xy. Okay, that's the definition. Exercise on Rn, all LP distances are equivalent in this sense. Okay, so that means that if you were to take two vectors, look at their distance relative to one of these p norms, you get to bound that distance by q norm, let's say, up to some constant, and from above and below. Here's another exercise. Now you see, in this case, I have the same set, different metrics on it. They possibly give me different numbers if I use different metrics, but if my metrics are equivalent, at least they are comparable. That's the idea. D1 and D2 are Lipschitz equivalent if and only if the identity map from X to itself is biLipschitz. So it is an inverse. I'm saying it's Lipschitz both ways. Identity function from X comma D1 to X comma D2 is biLipschitz. Okay, so it is Lipschitz from here to there and from here to there. Okay, so one of these inequalities, I mean, this isn't that complicated of an exercise. It's a logical exercise, if anything. So this really says that, so this is the input and this is the output, right? Which means that So this inequality really says that if you're going backwards from D2 to D1, identity is Lipschitz. And if you look at this inequality, it says that this is Lipschitz. So that's sort of the solution to this exercise. Okay. Okay. Another definition, slightly more general. X and Y are called biLipschitz equivalent, or lipeomorphic is a word that some people use, are lipeomorphic. So somehow they have the same Lipschitz structure. If there is a biLipschitz function from x to y that is invertible. Maybe I should write it like that more explicitly. There's a function, there's an invertible function f from x to y such that f is Lipschitz and f inverse is Lipschitz. Lipschitz, okay? That's another definition. Okay, I still haven't talked about continuity. I think it's time. A function between two metric spaces is continuous if you have the standard epsilon-delta definition hold. If for any points x, let's say x0, and for any epsilon, there's a delta such that for any x in x, if x is delta close to x0, then their images are epsilon close. Okay. That's a standard definition. Another important definition is uniform continuity. Now it's going to look very similar, but what you need to do is essentially from this perspective, all you need to do is to take this expression and put it to the end. Because when you're reading this, you're saying for any epsilon, for any x0, for any epsilon, there's a delta. When you say that, you're really saying that this delta might possibly depend on epsilon, and it might depend on x0. So let me write it like that. Delta might depend on x0 and epsilon. With uniform continuity, you still have delta depending on epsilon, because epsilon is your error margin if you want. It's expected, it's reasonable to expect that it's going to depend on epsilon, but it doesn't depend on the base point x0. So that means that it is uniformly continuous. Uniform means that it doesn't depend on the base point. That's what it refers to. Continuous. F, you see, I'm literally going to do the same thing. I'm going to write the same thing, except that I'm cutting this here and putting it over there. For any epsilon, there's a delta, such that for any x1 and x2 in X, if x1 and x2 are delta close, then their images are epsilon close. So now, this delta might depend on epsilon. It does not depend on x0 or x1. Okay. Exercise. Now we have a bunch of inclusions. We said that we proved that continuously differentiable implies Lipschitz. Let's sort of do something similar here. And probably that's going to be the last thing I write for today. I'm writing everything in this more general context, but when it comes to sort of thinking about things and coming up with examples, it's good to go back to single variable calculus. I'm just considering a function from 0 to 1 to r. And let's say that I have two exponents, theta prime, between 0 and 1. Then f is, what do I want to say? Okay. Okay. I guess we can include this. Continuously differentiable implies Lipschitz, implies, this we did, implies theta prime Hölder, implies theta Hölder, so you get to make the exponent smaller. Implies uniformly continuous. Implies continuous. Okay? And this is why people would write C0 for continuous. Okay? Because it's like the exponent to the 0. Which means that you want to have, you know, the farther you go here, the better your function becomes, basically. Okay? Any questions about this? Okay, good. I think we're done for this week. I'll see you next week. Thank you.